RSA is one of the first asymmetric crypto systems based on modular arithmetic and prime factorization. Let's review what we actually need for such a system to work. First, we need unique private and public key pairs. Then we need to have the private key undo the public key operation. It needs to be an inverse operator. And also, the private keys should be easy to generate but hard to crack. They should be based on a trapdoor function. So here's the basic idea with modular arithmetic. In the Diffie-Hellman key exchange, we were using the discrete logarithm problem to establish a shared secret key. Here we're going to use it to encrypt and decrypt the message. So the idea goes as follows. We take some message, raise it to the power of the public key, and take the modulus of some number such that we get ciphertext. And then, to reverse that, we would want to take this ciphertext, raise it to the power of the secret key to the same modulus, and then we want to get the initial message back. This simply translates to m raised to the power of the public key times the private key mod n will give us back m. So now the big challenge is to define this relationship between the public and the private key such that the private key can only be generated by the private key holder. It should be based on some information that just this one person holds. To understand that, we need some more math fundamentals. We're going to use something that is called Euler's totient function. It describes the breakability of a number. It's also called the phi function. The phi function counts the number of numbers smaller than n, let's say 8 in this time, which are not divisible by any other number than 1. So it's a number of numbers smaller than 8 which have the greatest common divisor of 1. So we have here 1, 2, 3, 4, 5, 6, 7. And we're going to check, okay, 1. Only divisible by 1, of course. 2 and 8, they're both divisible by 2, so this will not be counted. 3 and 8, they have the greatest divisor of 1. Okay. 4 is also divisible by 2, so that is not counted. 5 is only divisible by 1. 6 again is divisible by 2. And 7 again only by 1. So the phi of 8 would be 4. There are some interesting facts about this phi function. For example, the phi of any prime number is simply the prime number minus 1. Because a prime number is only divisible by 1 and itself, it follows that all smaller numbers than the prime have a greatest common divisor of 1, of course. Then, the phi function is also multiplicative. So, the phi of a times b is equal to the phi of a times the phi of b. Now comes the interesting part. We can link these two properties here on top to create something like this. We can multiply two primes and find the phi function of the result of this new number simply by multiplying the phi of the first prime number times the phi of the second prime number, which simply translates to the prime 1 minus 1 times prime 2 minus 1. And we get the phi of that new number n. This is the trapdoor function we're going to use. It's hard to compute a phi function of a big n without knowing the exact factorization. But it's easy if we know it. Then we can simply plug in this formula. To actually use this phi function, we need one more theorem and some simplification steps to actually get to the private key generator function. So Euler's theorem. It states a message raised to the power of phi of n equals 1 mod n. This we can modify because 1 raised to the power of k is still 1. We can just multiply the whole thing by the power of k. So we get m raised to the power of k times phi of n equals 1 mod n. Then we can multiply the whole thing times m, which will give us m raised to the power of k times phi of n, and simply plus 1 equals m mod n. Let's remember the formula we created to encrypt and decrypt the message. What we want to have is something like this. A message raised to the power of the public key times the power of the private key should give us m mod n back. Okay, now we can see here these two equal to the same thing. So we can set those formulas equal to each other, take the logs and solve for d. This will look like this. So it's pretty straightforward. You take the logs, set it equal, and then you divide the left hand side by e to get d. And this is how we're going to generate the private key. It is based on this phi function of n, which is hard to compute for anyone which doesn't know the factorization of it. Be aware that there are multiple possible values for k. These are just chosen such that d is going to be a whole integer. Let's test this with an example. First, we're going to choose two prime numbers and multiply them to get a new number n. Let's go with 11 times 7 equals 77. Next, we're going to compute the Euler's totient function, which is simply going to be 10 times 6 equals 60, which is the phi of 77. Then we're going to choose a random prime number smaller than the totient of n as a public key e. So some number smaller than 60. Let's go with 13. Next, we're going to compute the private key based on the formula we derived before, which was d equals to k times phi n plus 1 divided through e will give us d. Now this is going to work out for k equals to 8. So 8 times 60 plus 1 divided through 13 will give us 37 as the private key. Now let's encrypt the message with this scheme. To encrypt an initial message, let's say we want to just send the number 2, we're going to take 2, raise it to the power of the public key 13, and take the modulus of here our number n. This will give us 30. So this is the ciphertext. 30 is encrypted for 2. To decrypt this, we're going to take 30, we're going to take the ciphertext, raise it to the power of the private key, which is 37, and again take the same modulus, and we will get back to 2. Notice that in reality these numbers are much bigger. In this case, it would be easy to crack someone's private key, because with those small numbers we can still easily find the 5 function. If the numbers are huge though, it's hard to find the 5 function without knowing the factorization. That's the whole magic of this RSA scheme.